Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject, the topic already we have discussed in the previous session, Euler's column theory, the derivation and the assumptions, and about this column theory we have discussed. And in this today's session, once again we will see the column theory introduction part and then assumptions, and we will enter into the end conditions of columns part 2. So already we have discussed about this end conditions of column. There are four conditions are there. So both ends fixed and one end fixed and other end is free. Both ends hinged and one end is fixed and other end is free. So already three conditions are completed. In this today's session, the last end conditions we will discuss, and then we will analyze all these four conditions. So the course outcome is analyze the Euler's column theory and deformation of columns and struts. The student should be able to analyze this Euler's column theory after completion of this topic. So about Euler's column theory. So once again recall this column theory. The first rational attempt to study the stability of long columns as made by the Euler. He derived an equation for the buckling load of long columns based on the bending stress. Already we know, we have discussed about the buckling load of the of long columns and bending stress. So normally the column is subjected to compressive stress. So whenever the compressive stress exceed the ultimate stress, the column will be fail due to this compressive load. But always the entire column will not fail due to this compressive load. The column will fail due to the bending stress. So that is called as buckling stress, at which the column bends. That corresponding load is called as buckling load or critical load or crippling load. So long columns fail due to this type of buckling loads. So while deriving this equation, the effect of direct stress is neglected. So direct stress already you know you can calculate by using this empirical relation. The compressive load and area, cross-sectional area. You will get a direct stress. But this may be justified in the statement that the direct stress induced in a long column is negligible as compared to the bending stress. So by deriving the equation, Euler's equation, so we will not consider this direct stress. So next, what are the assumptions made in this Euler's theory? So the following simplifying assumptions are made in the Euler's column theory. Initially, the column is perfectly straight and the load applied is truly axial. The cross section of the column is uniform throughout its length. The column material is perfectly elastic, homogeneous, and isotropic, and it obeys Hooke's law. You know, the Hooke's law is stress is directly proportional to strain. So within the elastic limit, sigma is equal to E into strain. So the major assumptions are the material, the column material is perfectly elastic, homogeneous, and also should obey the Hooke's law and isotropic material. Always the column is perfectly straight. And always the load applied is truly axial. and the length of the column is very large as compared to its cross-sectional dimensions. So the shortening of column due to direct compression being very small is neglected. So the failure of the column occurs due to buckling alone. So whenever the column is like this, the load is acting. So the length of the column L is very large when compared to the cross-sectional area of the column. This is diameter. So the bend like this, or the bend like this. So the sign convention is also important. One is positive sign and another one is negative sign. Generally, we have commonly used signs are for concavity negative sign and negative, for convexity positive sign we will use. So types of end conditions already I told you. So there are various end conditions are there. So depends upon the structure end condition need to derive the Eulers column theory to avoid the buckling. So that is to calculate the buckling load. So end conditions are very important. You should know the end conditions of the column. So there are number of end conditions for columns. We shall study the Eulers column theory on the following four types of end conditions. One is both ends hinged, one end is fixed, and other end is free, and both ends fixed, one end is fixed, and other end is hinged. So already three we have completed. The fourth one is fixed and other end is hinged. That is pending. So we will see in this session. So after that, after completion of these four end conditions, we will compare. So the columns with one end fixed and other end is free. So sorry, other end is hinged. So already we have derived in previous session. One end is fixed, other end is free, and both ends fixed and also completed. So consider here a column AB, length L, fixed at A, hinged at B, and carrying a critical load is B. So initially the column is AXB, after bending AX1B. Clear? So the length L fixed at A and hinged at B, and also carrying that load B at and load P at B. This is hinged. So as a result of loading, the column deflect like this. So now consider any section x at a distance small x from A. It's already shown in this diagram. So let P is the critical load of the column and Y is the deflection of the beam at X. See, a little consideration will show that since the beam AB is fixed at A and is carrying load, therefore there will be some fixed end moment at A. In order to balance the fixing moment at A, there will be horizontal reaction at B. So the moment at A is fixed end moment at A, and H is horizontal reaction at B. The moment due to critical load, that is M is equal to minus P into Y. So the end conditions of the column shown in this figure. So the moment due to critical load is negative. So for convexity and concavity, negative and positive signs already we have used in previous condition. So here also apply same procedure and find out the Eulers column theory, the buckling load equation. When the column is one end is fixed, the other end is hinged. So now write down the equation EI into d square y by dx square is equal to h into L minus x minus p into y as shown in figure. So h, the hinged portion of horizontal reaction force, h into L minus x, so L minus x, and then p into y. So now simplify the above equation, d square y by dx square plus p by ei into y is equal to h into L minus x by ei. So now the general solution of the above differential equation is, so y is equal to c1 cos x into square root of p by ei plus c2 into sin x into square root of p by ei plus h into L minus x by p, where the c1 and c2 are the constants of integration. The values of constants obtained from the boundary conditions. The c1 and c2 will obtain from the boundary condition, and then after getting the c1 and c2 value, again substitute in this equation. So first at the boundary conditions, at a point x is equal to 0 and y is equal to 0, there is no deflection at a fixed end, and slope also 0 as a is fixed end. At b, that is hinged point, that is x is equal to L, and then there is no deflection, and y is equal to 0. When x is equal to 0 and then y is equal to 0 from equation, so you will get c1 is equal to minus h L by p. So in this equation, x is equal to 0 and y is equal to 0. Substitute the c1, you will get minus h L by p. So differentiating the first equation at x is equal to 0 and dy by dx is 0, differentiate equation we get dy by dx is equal to minus c1 into square root of p by ei into sin x into square root of p by ei plus c2 into square root of p by a cos square root of p by cos into x into cos of x into square root of p by minus h by p. So after substituting x is equal to 0 and dy by dx is equal to 0 in every equation, so substitute x is equal to dy by dx is equal to 0 and p by ei into sin 0 plus c2 square root of p by ei into cos 0 minus h by p. So cos 0 1 and the remaining all terms be 0. So c2 square root of p by ei is equal to 0. Therefore c2 is equal to minus h by p is equal to 0. So written here. So now c2 is equal to h by p into square root of ei by p. So we also know that when x is equal to L and y is equal to 0, So therefore, substituting these values x, y, and c1 and c2 in equation 1. In equation 1, substitute x is equal to L, y is equal to 0, and c1 already we calculated, c1 is equal to 0, and c2 is equal to h by p into square root of e I by p. So substitute in above equation, we will get the final equation after substituting y is equal to 0 and c2 h by p, hl by p into cos square L into square root of p by a. C1, C2 value substitute in this, and finally we'll get tan L into square root of p by a is equal to L into p by a. So you can write this equation like this: sin by cos sin L by a into cos square root of p by a, tan square root of L into p by a. That is equal to HH get cancelled here, PP also get cancelled. L into square root of p by a. So little consultation show that the value of L into square root of p by ei in radians. So it has to be such that its tangent is equal to itself. We know that the only angle, the value of whose tangent is equal to itself is about 4.5 radians. So that L into square root of p by ei is equal to 4.5, or L square into p by a is equal to 20.2, squaring on both sides. So you will get the p is equal to 20.25 a by L square. Taking the least significant value, p is equal to 2 pi square ei by L square. But in previous case, 4 pi square ei by L square, when the end conditions are one end is fixed and another end is free. But in this, one end is fixed, another end is hinged. So a little consultation will show that 20.25 is not exactly equal to 2 pi square, but approximately equal to 2 pi square. This has been done to rationalize the value of P, that is crippling load in various cases. So now the Eulers formula and equivalent length of the column. All the above cases are represented by general equation called Eulers formula, where L is the equivalent or effective length of the column. So already we have derived the equivalent load P in all four cases. When the both ends hinged, when the both ends fixed, one end is fixed, the other end is free, and one end is fixed, other end is hinged. The four conditions we have already discussed and derived the equations. So now we will see the equivalent length of the column. So there is another way of representing this, the equation for the crippling load by an equivalent length of the effective length of a column. So the equivalent length of the given column with given end conditions is the length of an equivalent column of the same material and cross section with both ends hinged and having the value of crippling load equal to that of the given column. So the equivalent length of the given column with given end conditions is the length of an equivalent column of the same material. So see, in this table shown the equivalent lengths for the given end conditions. The end conditions already we know. One is both ends hinged. Second one is one end fixed and other end is free. Third one is both ends fixed. And the fourth one is one end fixed and other end is hinged. So what is the relation between equivalent length and actual length? So the equivalent length is LE is equal to L. So when both ends injured, that crippling load already we have derived. The P is equal to pi square E I by L square. So this is the both ends injured condition. So the pi square E I by L square. So this is equal to L. When one end is fixed, other end is free. The equivalent length is, you can write the relation between the equivalent length and the actual length, LE is equal to 2L. So the pi square EI by 4L square is the final crippling load equation. So the pi square EI by L square is the actual length. So you can write this equation, pi square EI by L square, LE is equal to 2L. Both ends fixed. The equivalent length is L by 2. Here, see, in this equation, the pi square EI by L square. So this is the original length, the actual length. But in this condition, 2L. So it means the equivalent length is equal to 2L. That is LE is equal to 2L. 2 times of the actual length. Similarly, in this condition, both ends fixed. Already we have derived the power pi square EI by L square. In the case of L by 2, that is L, so L is equal to L by 2, the equivalent length. Similarly, one end is fixed and other end is hinged. So 2 pi square by EI by L square. You can write pi square EI by L by 2, L by root 2 whole square. So this is L, the actual length. So that, sorry, this is LE is equal to L by root 2. So these are the equivalent length for the given end conditions. Up to now, whatever we have derived. So the equivalent length of the given column with given end conditions is the length of an equivalent column of the same material and cross section with both ends hinged, having the value of the crippling load equal to that of the given column. So the LE is the equivalent or effective length of the column represented by general equation, that is called Eulers formula. So already we have discussed. So up to now we have completed the Eulers column theory and then different end conditions. So how to write the Eulers for theory for buckling load, crippling load or buckling load. We have calculated by using Eulers column theory equation. And then we have discussed about the equivalent lengths for the given end conditions. also have derived, and the final comparison between these four, both ends hinged and one end is fixed and the other end free, and both ends fixed and one end is fixed and other end hinged. These conditions already we have compared in the form of equivalent length. So the relation between equivalent length and actual length also we have simplified. Suppose you take the both ends hinged. So what is the equivalent length? So the actual length is L. So in both ends hinged case, the equivalent length is L only. Same length. There is no change. But by solving problems, you need to substitute the actual length, the given L only. But while solving problem, suppose the condition, the end condition is one end fixed, other end is free given. In the case of how do you calculate the equivalent length? Equivalent length is equal to 2 times of the 2L. 2 times of the 2L. 2 times of the L. Need to substitute like this. Similarly, both ends fixed. The end condition they will give in a problem. We will see while doing the problem solving session. So L is equal to L by 2. So one end is fixed and other end is hinged case. LE, the equivalent length, you need to substitute L by root 2. Need to take the L by root 2 value. So the given value is suppose 400 mm or 200 mm. So L by 2 means you have to 100 by 2. Need to substitute 51. That is depends upon the given end condition. So that the Eulers column theory is derived on some assumptions, and also it depends upon the nature, the condition of the end condition of the column. So while problem solving, we will discuss again all these things. So there are differences I have taken for this PPT. S. Ramamrutam, Strength of Material, Dhanpeth Rai Publishers, and the title of the book is Strength of Material. R.K. Bansal, the title of the book is Strength of Material, and R.S. Kurmi and Gupta, Strength of Materials title. The publishers are Chand and Co. So these are the references I have taken for this PPT. You also take one reference for other more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.